Hello, everyone. I am delighted to give this lecture in the course Dynamics of Solid and Fluids, which is about conservation of energy. So you have so far seen the general scope from translating nature to mathematics, and then we discussed about a series of conservation laws that would allow us to translate different parts of the processes that are involved in the nature. First one was conservation of mass, and then conservation of momentum. Now I am teaching you conservation of energy. So let's get started. The energy conservation law tells us that change of the internal energy U of any closed system is equal to the addition of heat in the system or work that has been performed on the system. So if we have a system that does not have any heat exchange with external environments, or no work is done on it or performed by it, then its internal energy cannot change. The du will be 0. We can write the same equation per mass, per unit mass, which in this case, all the capital letters would be written with small letters, and they all would mean the quantities per mass. For example, you can consider the fact that you have a unit kilogram, unit mass of the system. That unit mass internal energy will change only if some heat exchange takes place with that system or work being done by it or on it as well. So now this is quite important, which would then mean that we can work a little bit further on this subject and obtain processes in the nature, especially in Earth ecosystem, that happen relevant for this sort of energy conservation law. For example, change of the energy, internal energy of the system is du, which is again per mass, and that is equal to the heat capacity at constant volume, which is this CV, times the change of the temperature. So if you have a unit mass of a system, if you start, or per unit mass in a way, if you heat this system, its internal energy will increase. That would cause change of temperature. Internal energy change is proportional to the change of the temperature of the system. The proportionality factor is CV, which is constant volume heat capacity. How about the work performed by the system or on the system? The way that we have written it, dW is at the right-hand side. That would then, if you perform work on the system, it would cause increase of its internal energy. Now imagine a parcel, a cylinder at constant pressure. If it changes its volume, then there is a work performed by the system. And the work performed on the system would be the negative amount of the same amount of work. So let me go to my board and explain you in this way. So I have a cylinder which has a piston on it like this. Now, if the volume here changes, this volume, changes at constant pressure P. Let's say I bring it to the higher level. So then the work, the small amount of work that has been performed on the system is minus pressure change of the volume. Why minus pressure? Pressure is a compressive force, and so the tensile force that we want is the negative of the pressure. Or we can say that the work performed on the system is the negative part of the work performed by the system. And so you would see that if we have the pressure here acting, the work performed on the system is minus P dV. Now, we just spoke about the fact that we have du, change of the internal energy of the system, is dq plus dw. And I just explained to you that if we expand the system by d volume under constant pressure, the work performed on it is minus pressure dV. That would then require us to write the change of the work or the amount of incremental work performed on the system as minus P dV. And so I can use these two terms and substitute it in the conservation of energy for closed system. And that would mean that I can write my Q, heat added to the system, small heat added to the system, as du, internal energy, minus the dW. And that would mean that du minus dW would be the change of the exchange of the heat, or heat added to the system. Now, what is du? Du is constant volume heat capacity times change of the temperature, CV dt, minus dW is P dV. So I end up with a formula that would tell me that the dq is CV dt, that's the du part, plus P dV, which would be the dW, which is work performed on the system. Given these terms and being imbalanced, now if no heat is added to the system, if no change of volume takes place in the system, change of the temperature will be zero. It's exactly like saying that the internal energy of the system would not change. Okay, now let's consider two different cases. One case would be constant volume change, another would be constant pressure change. In order to do both of them well, let's look into the gas law before we start doing those two cases. Gas law says the pressure, which is equal to rho RT, so remember PV is an RT, so you write it for per mass, basically. So you would get P is rho. Imagine this is N divided by volume. P is rho RT. And you can actually rewrite this equation by bringing rho to the left-hand side, which would be then 1 divided by rho, and that would mean V, specific volume. So rho is 1 divided by specific volume V. So in that case, I can write the same formula as PV is RD T or RT. And if I do the chain differentiation law, that would mean that PdV plus VdP, which is the differentiation of the first term using chain law, is equal RdT. So why would I do that? It helps me correlate the constant volume or constant pressure processes with the RdT, the change of the temperature, which is pretty much measurable. Let's see it in practice. If I have a constant volume process, change of the internal energy of the system, which was CV dt, and the work performed on it would balance with the heat added to the system. So heat added dq is CV dt plus pressure volume change. Now, since it's a constant volume process, PdV will be zero because it's a constant volume process. And therefore, I get dq is CV dt, which is pretty straightforward. Now, how about constant pressure term? Let me just go to my notes and say constant pressure process. In this case, dq, which was CV dt plus pdv, should be now written based on dp, because it's not a volume constant process that dv would go to zero for. Now here is dp is zero, not dv. So I rewrite it as CV dt plus, now I need to write pdv, but as I said in the gas law, p dv plus v dp was rd dt from the slide that I just showed. So I am going to substitute pdv here. This is my pdv with this term, which is equivalent here. And so I would like to write it as rd dt minus v dp, because that's precisely the term that remains here and is equal to pdv, this term and that term. Very nice. Isn't it constant pressure process? That would mean that dp is zero. And that would mean that my dq finally will be CV dt, constant volume heat capacity times change of the temperature, plus RD dt, the gas constant times dt, which can be also further processed as CV plus RD times dt. This term, constant volume heat capacity plus R, is defined as constant pressure heat capacity. Heat capacity, constant pressure. So I am going to finally write as dq will be Cp dt if the process is constant pressure process. So if the process was volume constant process, it would have been Cv dt, change of heat flux or heat added to the system. If you add heat to the system, it would be Cv dt. If the process is constant pressure process, pressure stays constant, change of the temperature based on heat added to the system will happen with the correlation factor of Cp, constant pressure heat capacity. Now, let me explain to you what do they mean. If I have, let's say, a kind of boiler. Now, imagine this is fire. This is fireplace. I have a kind of a cylinder which has fixed piston here, and this is fixed. If I add the heat to the system, so dq will be added here, change of the temperature will happen based on constant volume process. Now, if I have the same oven now is heating up now another system which has a kind of sliding piston on it, and there is a weight on it that would then always stays with the same weight, the piston cap, and so the process would be always constant pressure. And if I add heat on it, it actually expands too. So it comes to higher level with this amount. That process will cause the change of the heat added to the system to go through Cp dt, constant pressure heat capacity dt. Constant pressure heat capacity, as you can see here, is bigger than constant volume heat capacity, which means Cp is bigger than Cv. So for the same amount of Q added to the system, change of the temperature, if it is going through constant pressure process, would be smaller because Cp is bigger. So a smaller value should be multiplied by it to give you the same dQ. So if you have a process in which when you add heat to the system compresses or expands based on its compressibility and is allowed to expand, then the change of the temperature would be smaller for that system compared to the case that you would fix the volume and would add heat to it. Because the term of dW in that case of constant volume would be zero. But constant pressure would allow the system, when it's getting heat, increase its temperature, but also expands its volume. And that is why in total in the process, dt of constant pressure process would be smaller than constant volume process. So if I go back to my slides, you will see that that was the constant volume process. And if I go to the same notes that I just did by hand here in my notes, you start by writing for constant pressure process, you will correlate PdV as R dt minus VdP. And so since the pressure is zero, you only are left with RD dt. You factorize the change of the temperature. There is a dt missing here. Then you would get finally Cv plus Rd that is defined. It is defined as the constant pressure heat capacity. That is actually quite a very important part of the story that we are going to discuss about. Now imagine we have an isolated air parcel. There is an air parcel here that is isolated, is a bucket of air. That bucket of air can elevate itself, it can rise, it can come down. And imagine we would like to write conservation of energy for it. So if this parcel goes high or comes to lower elevations through a constant volume process, its change of dQ, the heat added to it or heat exchange in that system, would be Cv dt. However, if it goes based on constant pressure, change of its temperature would be correlated with the heat added to this bucket of air with Cp. Now, as we said, Cp is bigger than Cv. So we are wondering, would air, the bucket of isolated air, when it climbs, would it go through a constant volume process or constant pressure process? Yeah. So if a given amount of energy is added to an air parcel, imagine through radiation, imagine through all the processes that can happen, air, when it climbs or comes down, it actually changes its volume. So since air expands, it's compressible, some of the energy that is given to this parcel will be used to change its volume. And so work will be done by this change of the volume. Now, if Cp, the constant pressure heat capacity, is bigger than CV, which is always the case. It is the case. So if the bucket of isolated air goes up with a constant pressure process, its change of temperature would be smaller than if it would go with constant volume process, like the exact discussion that we just had. What is going to happen in the nature? If an air bucket is there, if it climbs, would it go through a constant volume process, or it would go through a constant pressure process? It is the fact that the air parser will change its elevation, either high or low, through a constant pressure process. So you would always use Cp dt to find out the heat exchange on that parcel and the consequences of that heat exchange to the temperature change of that parcel. So as air expands or compresses, work will be done. So we do dq to be the Cp dt and not anything else, not the CV one, right? So that's pretty much important. And then you can now go even forward and find out more sciences that would allow you to understand now what is exactly the change of the temperature of the air parcel as it climbs up or comes down. So I will start to pause the record. Okay, so we just obtained the fact that in the atmosphere, when an isolated air parcel climbs or comes down, it goes through a constant pressure process. And as such, the dq for it would be Cp dt. And so the change of the temperature for it would be smaller than the change of the temperature of an air parcel that would go through constant volume. Since it expands and compresses, it is going through a heat consequence of the heat added to it or released from it would be to change the temperature through a constant pressure process. Okay, and the Cp is already around 1,004.7 if you want to be clear. If you want to have an estimate of it for air, you would just get it around 1,000 joules per kilogram Kelvin. Okay, now let's see. How would this change of the temperature will take place? Let us define an adiabatic parcel, which is defined as a parcel that does not mix with its environment and does not absorb heat by the environment. For example, there is no radiation. So it's an isolated adiabatic parcel which does not mix. So it doesn't have any mass exchange, nor would it have any heat exchange with the external environment. And so its temperature could change. The temperature of this isolated parcel of air would change if it changes its altitude, say climbs or comes down, or some condensation of, let's say, water or evaporation would happen. So in a way, phase change takes place in it. Some droplets of water gets there, or some water that was in liquid form now becomes vapor. So heat exchange takes place. So latent heat would happen internally with it. So for this parcel, change of the Q, so heat of water, let's say condensation, if water condensation takes place in this process, because there is no other heat to be added to it or released from it, except from condensation or evaporation, it will cause change of the internal energy through the constant pressure process that we have already discussed. So internal energy, including expansion, etc., will be already there because it's a constant pressure process. And also, since it can change its elevation and it can climb by amount of, let's say, dz, since when it climbs, it gains the potential. So then the g acceleration vector is downward while the dz is upward. So there is a negative point in here. So pressure actually decreases as you climb up. So in that case, change of the pressure as you climb dz will be minus rho g dz. It's like hydrostatic pressure. And so based on the conservation of energy, I have the Q term here. I have the internal energy and the work on the constant pressure process here. But there is another work that is to be done, which is by change of the elevation. And that would be related to change of the pressure divided by the density. We are writing everything per mass. You could also multiply everything by density, so you would get it for the density-based system. Here we have minus dp over density. Now, if we know dp is minus rho g dz because it's elevation change in the atmosphere, then I can actually write my minus dp divided by rho to be minus dp. From here, dp is minus rho g dz divided by rho, and I end up with g dz, which is exactly written here. Cp dt stays the same. That's internal energy through a constant pressure process. And now imagine condensation takes place. So I have the latent heat for the condensation of 1 kilogram of vapor water to become liquid. And then I have the entire dql for the condensation here as well. This multiplication would give me the total heat per mass that is released by condensation. Because when I condense it, I release energy. That energy can increase my delta T, if you see it in here. If I can show my pointer, yes. So imagine my condensation would release this much energy. That energy would cause change of temperature if, for example, the elevation would stay the same. Now, if I don't have any change of the condensation or evaporation happening, no phase change, if I climb, I will change my temperature. How interesting. Now I can actually study, if I change my elevation, how much my temperature will change, all from simple conservation law. So let's move on to that point. We got so far that the heat released by the condensation will cause either change of the temperature of my system, or I can just compensate with it by changing my elevation. Nice. What would it mean? Now, imagine my system is dry. My air parcel does not have any condensation or liquefaction. Condensation or evaporation in it, right? I don't have any of those here. If I don't have any condensation or evaporation, I can assume that LVDQL, which is the latent heat, LV is the latent heat for the condensation, imagine that would be simply 0. That is not going to take place. I change my elevation, but no condensation takes place, no evaporation takes place. So that LVDQL, the DQL is 0. Then what will happen? My change of internal energy through the constant pressure process, plus that small work that is being done, or whatever it is because of the compression, and there is a kind of PDV in it as well, with the change of elevation would balance each other. That's very, very interesting. Because now I can say for a dry parcel, change of the temperature is proportional to the change of the elevation with a factor of G divided by Cp. Because now I can write my Cp dt plus G dz is 0. Therefore, my dt divided by dz, so I'm dividing everybody by a dz factor that goes away from here, and then I have it for this one in here. Then I put G on the other right-hand side, which will be minus G divided by Cp. Fantastic. It means if I change my elevation by 1 kilometer, which is 1,000 meters, you can now estimate how much of temperature will change. As I said, Cp can be approximately set as 1,000. G is roughly 10. 10 divided by 1,000 is roughly minus 1 over 100. That's quite an impressive number, meaning that 1,000 meters elevation climb would cause about 10 degrees of temperature change. That's quite nice, right? We are getting to know about the conservation of energy consequence on how the temperature of the atmosphere would look like, roughly. We have neglected some other heat exchange processes by the way, right? Fantastic. Obviously, that would be the change of degree of Kelvin, or Kelvin in a way over meter, for example, right? So there's a unit for it. dt, T is Kelvin, Z is meter. Very nice. And that's exactly what I have written here for you. Now I move on and then say, let's start from T0, some reference temperature, which is happening at elevation 0. So I have an elevation reference that is Z is 0. Temperature there is also T0. And I climb to elevation Z, which has its own temperature. So I integrate my ordinary differential equation, which would then say that Cpt plus Gz, this term, simple integration, will be Cp T0, which is constant. And that would be exactly what I would need then to say that, well, you know what? If I want to know about my temperature at a given elevation, I need to say that the temperature will be some constant value, let's say C is some constant, I can call it as C1. For example, that's a constant value. What else? Minus G divided by Cp times Z. So for any given reference, so that Z0 will be T0. So then I will, instead of writing it as C1 or constant, I write it T0. So from any temperature T0, I start, and with the slope of GCP, I decrease my temperature as I climb upstairs. And if I go 1,000 meters up with gravity around 10 and CP around 1,000, you can estimate how much my temperature will be lower now. Now, imagine you're flying with an aircraft. You're about 10,000 meters above the ground. 10,000. How much temperature should drop? And think about, is this typical? Is this the temperature that you would observe when you are watching your flight schedule and flight information on your screen? Do you see that much temperature drop? And if not, what do you think the consequences, that the discrepancy is coming from? And can you explain that to us? That's also an important topic. Okay, so far we have seen that the latent heat released by the condensation would be compensating itself with Cp dt and Gdz, which is the internal energy and some work, and then also elevation change as well. Work to actually change your elevation. That's G dz. CPdT is the internal energy through the process of constant pressure, and it has also some D work in it already too. Now, we move on to getting to know what is the latent heat released by water condensation. If 1 kilogram of water condenses, it releases 2.5 million joules of energy. Yeah, that's the meaning, that's the value of latent heat for condensation. In the saturated case, when we have condensation or evaporation taking place, we cannot neglect the LVDQ term. We cannot neglect the fact that I need to find out how much energy it would cost me or release when I evaporate or condense this amount of mass of water in my system. Yeah? Multiplied by mass quantity, that would be the total heat released or gained through this condensation process. So I am now in my previous integral, I am also now including the latent heat related to phase change, related to condensation. And I brought the LVDQ to the other side, so that's why it has a negative sign in here now. And I do the mathematics of it. CPdT integral is CPT. Constants will go all the way to the right-hand side, which is this constant. Then I have GZ. Then I have LVDQ with the negative sign. And that is all constant, the constant of integration, right? And that constant is called the SL, okay? So that's the process. This whole thing now is constant when we have the condensation or evaporation taking place. So it's not that CPT plus GZ is constant. When we have condensation or evaporation, considering the LVDQ, the total heat released with the condensation, that's then the total amount of the total would be conserved or constant. So S dry is when we do not have any condensation evaporation. In that case, LVDQ is 0, and that's then S dry would be constant. When we have saturated case in which condensation evaporation takes place, then SL would be constant. So that's also something that we have introduced as terms that would also make it simple for us to understand the process. Now, how can SL change? If we have condensation, evaporation, and change of elevation and change of internal energy, all of these terms are considered already in these 3 terms. What else can cause change of energy of your parcel of Earth? One example would be radiation. We neglected radiation totally so far in our conversation. Radiation is another form of heat exchange. So change of SL, change of your energy in the wet system, in the system that has latent heat of condensation or evaporation, will take place if you also have radiation in the system. If you radiate heat through the system into the system, you can then change its entire energy. And energy conservation holds. So it's not about only condensation, evaporation. It's not just about the work done by expansion because air is compressible. It's not just because of the work done by change of the elevation. It's also because radiation takes place. We neglected that, but if we add it to it, again, it would be simple mathematics. We need to add the amount of radiation heat flux into the system. So we account for the right energy balance in our system. That's pretty much all of it about energy conservation in the atmospheric science related topics, where we understand that the change of internal energy would be equal to the heat added to the system plus the dW, the work done on the system. And then for the specific case of an isolated adiabatic parcel of air, we wrote the energy conservation. And for that, we said if there is no condensation or evaporation, then we find that CPT plus GZ is constant. And from that, we can find out how the temperature of that parcel changes as we change the elevation with the rate of minus G divided by CP. If condensation or evaporation takes place, we add also LVDQ in the system, and then the entire term, cluster of the three terms, would be constant because latent heat would also play a role here. Now, with that, we would go on and see how this energy conservation, which we just described and discussed in the atmospheric sense, would be relevant for another Earth system process, which is the subsurface porous system, which would then be relevant mostly for, let's say, geothermal systems, processes like energy storage that would require energy balance. Many of them would require energy balance. CO2 storage, in many cases, it requires energy balance to be written because CO2 is in supercritical state. It expands, it does work, it gets heated, it releases heat, etc. In terms of hydrogen, in terms of other processes that take place in the subsurface, energy balance also matters there. So from atmosphere, we go to underground. And we do that for the same physics of understanding how du equals dq plus dw would be written now for another system, which is subsurface. If we look into the Earth crust, which is the upper part of the Earth, we see that when we dig deep in the Earth, temperature of the Earth layers increase and increase and increase. Depending on where you are, the slope can be steep, it can be slow. So there are cases in which you can go, let's say, 2 kilometers under the ground. Some places you can get 100 degrees rocks. In some other cases, you may get nearly 50-degree rock, depending on whether you are in volcanic zone, non-volcanic zone, etc. That would mean that heat is an essential part of anything in the subsurface, because subsurface is warm, much warmer than the surface. So we should also consider heat in the subsurface, or in a way, energy conservation in the subsurface processes. Imagine I go and drill a double well in which I am now injecting cold water here, and that has to become warm and produce warm water from the other side of the system. So this production of hot water induced by injection of this cold water can be also studied with heat balance coupled with the flow in the porous system of the subsurface formation. There are many, many processes that take place in the subsurface for us, for example, to extract heat. You can have conduction-based heat exchangers that extract heat from the subsurface through conduction only. They can be also from convection and extraction, for example, of heat, hot water. You could also go deeper in the subsurface and enhance the recovery of the heat by also cracking the rock and making it more permeable so that you can extract heat more efficiently and also reach higher degrees. Okay. Now we do the mathematics of underground energy balance equation. Now, compared to that adiabatic isolated air parcel, subsurface processes are open. Flow comes and goes away. So I have a control volume like this one that I'm plotting for you, in which there is an influx of energy. I call it with H dot N. H standing for enthalpy. And I have outflux of energy from that system. The same system has open boundaries, it's porous. And also there might be some external work on it that I'm going to most of the time, if not always, neglect. And there could be heat added to the system that is now being shown by this Q dot. A typical system in the subsurface open, obviously external work will be neglected later on as well. So I write the conservation of energy now for my system, which means that internal energy, change of internal energy, which is dU, should be dQ plus dW. So what is dQ? What is the heat added in my system? First process is incoming and outgoing flux of heat. Warm water comes, cold water comes, etc. So rate of energy in minus rate of energy out is the total energy incoming to the system. If whatever comes is equal to whatever goes, the net is zero. If whatever comes would not leave, would all stay, it all will add to my internal energy. And then there must be some consideration of external heat, Q dot here, that may be added to the system from external sources. Imagine I drill a well and inject cold water or warmer water, then I'm adding from outside something into my control volume. And if I do any external work, I need to also take it from my system too. Now, what is the change of internal energy? For the total system with the given density that I have, change of internal energy of my system is Cp dt, that's the thing that we already just discussed, times density. Now, I like to multiply things with density instead of dividing by density here. So that's just typical approach in the subsurface process. So I have the total U, change of the entire energy, will be rho C delta T, right? And since I'm approaching it as a control volume based, in a way, I am writing it for a unit volume. And then I need the mass of that volume, which would then require me write density times C delta T. Yeah? I am not writing it per mass here, in a way. I'm writing it per volume, and then that would require me to know how much mass I have in that volume. Okay. So what is net incoming heat flux? That H in minus H out dot means rate of energy coming minus rate of energy going, leaving. Now the question is, what are the mechanisms that heat exchange takes place in the subsurface? What are the mechanisms for heat transfer in the subsurface that I should consider? The first of this type of heat flux is through conduction. Conduction is a heat exchange process that does not need any movement, any velocity at macroscopic level. It actually takes place when I have change of temperature, gradient of temperature, between, let's say, any surface between left and right boundaries. If the temperature between left and right boundary of a solid or liquid or gaseous material, matter, is there, then I will get a flux of heat from high temperature side to low temperature side. That is called the flux of conduction heat. Heat flux of conduction. And that would mean that conductive heat flux will take place with the heat conduction coefficient, lambda here, and the gradient of temperature. And it would go downward with the temperature, which means it happens from high temperature to low temperature. So we multiply by a negative sign too. If I write it for this element that I'm showing here, Gradient of delta T times minus sign is nothing else than just writing T left minus T right divided by L. That's for that 1D element, the definition of gradient with a negative sign. Left minus right. If it was not with negative sign, it would be just gradient T, it would be T right minus T left divided by N. Since it's minus gradient, it will be T left minus T right divided by N. Heat conduction coefficient is lambda. Yeah. And if lambda is high, we have the same T left and T right with high lambda, a lot of heat conduction flux will take place. If lambda is low, very little heat conduction flux will take place. If we have the same heat flux, if lambda is high, the delta T, T left minus T right, will be small because the multiplication with lambda should give you the same Q. If lambda is a small, you will see a lot of differences between left and right. So for the same Q, for the same heat flux, or I'm calling it F here, so for the same F flux of conduction, if lambda is very high, then the delta T, if flux is constant, if lambda is very high, then the T right minus T left, or T left minus T right, which is the delta T, is very small. Because multiplication of them should give you the same Q. If for the same flux of conduction, if lambda is very small, then the delta T will be very high, which means left and right will have very different temperature values because lambda is very, very small. And that's exactly the definition of isolators. Isolators make the right side do not understand what the left temperature is about because they are perfect isolators. They cause very big, giant temperature gradients. Yeah. There are some questions here I'm leaving for you. Does conduction need mass transfer? What is the conduction coefficient for water, for metals, for wood, for different things, for rocks? And what is the conduction coefficient for a porous system? Imagine I have a rock, a porous material, which has some grains in it and some void space is there. So porosity part of it is the void volume percentage. And 1 minus phi is actually solid fraction, volume fraction. What would be the conduction coefficient of a porous sample when it has 5% fluid, 1 minus 5%, or 100 minus 5 solid? That's the definition of effective conduction coefficient. Effective conduction coefficient would mean that I have porosity, lambda F, which is, that's the amount of fluid that I have in the system, and then it would be based on the conduction coefficient of the fluid. 1 minus phi is the solid fraction in the system, and so I would use the conduction coefficient of the solid. And so that if I have 50%, then it would be half of fluid conduction coefficient, half of the solid conduction coefficient. That would be the total effective conduction coefficient of my porous sample. Okay, what else can happen? Apart from conduction, I can also have convection. Convection is happening with the fluid flow stream. Imagine you are sitting on a carrier that flows with some velocity. You are transferring heat, energy, mass together, and so it enhances the heat flux in your system. So if you have a velocity U, then the enthalpy, energy content of your system, of your molecule of, let's say, water, for example, in the geothermal system, would be needed to be multiplied with it, and so it would give you the convection heat flux, not conduction, convection. And if I write enthalpy here based on the delta T, I will get density, heat capacity, delta T. Now, what is heat capacity? Capacity of water, fluid, or solid, or effective. Solid does not move, does not flow. Flow takes place in the porous media only by the fluid. So the heat capacity that I use will be only for the fluid, and that will be multiplied by the fluid velocity, Darcy velocity. That will be discussed in the later lectures. So with the convection process, I am going to have a complementary now heat transfer with the conduction that takes place in the subsurface. Do we have other forms of heat exchange in the subsurface heat transfer? Well, radiation is very little. We don't consider it typically in our subsurface processes. And most of the time, these are the main mechanisms that we consider in the subsurface. Now, what I would like to do is I would like to go to a 1D porous media system and write down the heat or conservation of energy for that and find out what is the temperature distribution in my system, depending on how strong conduction is, how strong convection is. And so I would write a 1D conduction convection equation in which I have in the porous samples in many places in reality, and that would also help us understand how the temperature distribution in the system is. It's very much similar to what we did in the atmospheric science part, in which we wanted to know what the temperature of the air parcel would be if I climb 1 kilometer up or bring it down 1 kilometer lower. So after this break, I'll be going to mathematical formulations related to 1D flow of thermal flow in the porous system. Okay, so I'll be back in a second. Okay, let us consider a 1D system. That can be, for example, a 1D porous rock, which is experiencing fluid flow with heat transfer as well. Let's write conservation of energy for this open system. It's an open system. Flow comes, flow goes. So I have accumulation term first. Change over time of the amount of internal energy of my system, which will be density, C, and temperature. That's the accumulation term or internal energy. Plus net outgoing flux of heat. Net outgoing flux of heat. Net outgoing mathematically is out minus in. And if I write it mathematically, it reads with divergence operator, which is net outgoing heat flux. The first heat flux I'd like to consider is convective heat flux. Convective heat flux would be density of the fluid, because convection happens only for the fluid, heat capacity of the fluid part only, temperature of the fluid, and velocity of the fluid. That's the convective heat flux. And that divergence operative would say net outgoing. Net outgoing. And then I have another mechanism, which is conduction. And it happens for both fluid, and rock. Conduction takes place for both of them. So I have minus lambda grad T to be the conductive heat flux, and I need net outgoing of it, so I insert a divergence operator on it too. So that would be the conductive heat flux with negative sign of it to be outside. So I would call it as conductive heat flux, or to be, since the negative sign is outside, I write the entire as net outgoing conductive heat flux. So the rest is there. That will be equal to any source of external heat. So I call this as source of external heat. Assume there is no external heat in this system. So let's assume no external heat exists, or no external heat is added. That would mean that therefore Q is 0. That simplifies mathematics for us. Now let's study that for our porous system. The heat, convection, and conduction, therefore, are the main sources of heat exchange that we have, which is fantastic. For our porous system, for our porous medium, we should work out and find out what is the internal energy, what is the conduction, what is the convection. What is the rho C, which is the heat capacity multiplied by the density? That is, since it has internal energy of fluid and solid, then it is porosity, the amount of fraction, volume fraction of the fluid, then internal energy of the fluid, which would then require rho FC fluid, plus 1 minus porosity, rho solid, C solid. That is the rho C part in my equation for porous system. How about convection? Convection is only for fluid, so I write it only for fluid. How about conduction? Conduction is both for fluid and for solid. So the lambda, therefore, is porosity, as I spoke before, conduction coefficient of the fluid, 1 minus porosity, conduction coefficient of solid. So that's exactly the lambda up there. And I can actually now rewrite the equation that I have written up in here into a cluster equation, plugging all these terms. Yeah, so I can plug them all and then do the work in here. So what I'm going to do is I am going to put the equation, assuming that rho C is constant. Assume rho C is constant. Then I can plug it outside and divide all the equations by it, and assume also lambda is constant. And what else? Assume rho fluid C fluid is also constant. Then I can take all these factors out and do the mathematics easy. Q is also assumed to be 0. That's also nice. So that would mean that my 1D simplified equation that is done for my understanding of the process will be written as change of temperature over time plus convection was for rho fluid C fluid divided by rho total, C total, which is porosity rho FCF plus 1 minus porosity rho SCS, times the velocity U of fluid, because it's convection, it's coming from that equation in here, times T. Now I'm writing it for 1D system. That would then mean that I write it dt dx. That's the divergence operator T. So for 1D system, so I'm writing it for one-dimensional system, the divergence T for 1D system will be written as dt dx. And then I have conduction, which is minus lambda, and I'm dividing everybody by rho C. So I divided by rho C, and then I have two operators, one gradient, another divergence. So both of them together will make it second derivative of temperature with respect to x. That is 0 because source term is 0. That is my key equation at this moment. Now I want to describe and introduce rho FCF over rho C as R to make it just simpler. And I call the lambda divided by rho C as D, the coefficient D. Yeah. So if I want to be even more accurate, R will be rho FCF divided by rho C. What is rho C? If you can tell me, it is porosity rho FCF plus 1 minus porosity rho solid C solid. D is lambda over rho C, which is porosity lambda fluid plus 1 minus porosity lambda solid divided by rho C, which is porosity rho FCF plus porosity rho solid C solid. Very well. Now I can write my equation finally as dT over time, change of temperature over time, plus R U fluid dt over dx minus the second derivative of temperature with respect to space is 0. This term represents internal energy. This term represents convective heat transfer. This term represents conductive heat transfer. There is a little bit of point here that I would like to skip at this moment, and later on I'll speak about it, that convection is taking place not with the velocity of the fluid, but with R times U fluid. And R is smaller than 1, except if porosity was 1. So R is less than 1 or equal than 1 in the case of porosity 1. So convection takes place with the velocity F times R. And there is a physics behind this or understanding of this in more details. Conduction is also here. As you see, conduction is with second derivative of temperature. Convection is more of first derivative of temperature. And so I'm going to explain a bit more on these to learn about it. But before we move on to this, I'd like to remind you that this is a partial differential equation. As you see, there are partials. Temperature is a function of x and time, space and time. So that's great. It's PDE. And it's a kind of a mixed. If we have only convection, that's one type of PDE. If we have only conduction, we have another type of PDE. And now that we have both of them together, we have a mix of those type of PDEs in place. Okay, so I hope that so far everything was clear to you and you could get to understand where we started from and where are we now in this process of obtaining a conservation equation for an open system of porous medium with conduction and convection in place. That helps us understand temperature as a function of x and time. So for a given time, inside our core rock, instead of our porous medium, we can see how the temperature would, for example, be distributed. In each time, it would be, for example, different, right? We are going to now focus on this equation and discuss about some key aspects related to it. And then later on the practical session, we will also develop a solver for it so that we plot the distribution of the temperature given the specific physics. Okay, so now let's do the final part. I have a convective conductive energy balance equation for 1D porous sample here in front of you. Now let me consider a few cases. Case one. Case one will be the case that the situation that I have no convection taking place. No convection. Therefore, the second term here will go away. And my governing equation will be d dt, change of temperature over time, minus d second derivative of temperature with respect to space is 0. That's what I would get. This is a parabolic partial differential equation. Parabolic PDE. Parabolic PDE means it's global. If you change temperature in one location, all locations will understand, and it takes time till everybody feels the change as well, fully. But immediately they understand temperature has changed, it takes time till the significance of it reaches to the steady state and become all the maximum impact that they would get from that change of temperature. The profile of heat, or better say, the profile of temperature, if I had initially my system, let's say at this constant temperature, so that's temperature with respect to x, imagine suddenly I bring the left boundary to contact with very high temperature. I increase the temperature in the left boundary. Because it's a parabolic problem, we can solve it analytically for known functional value for d. The temperature profile looks very much diffuse. As time passes by, you will see that temperature would look like this if I have fixed t left and I have fixed t right. Very diffuse, very much parabolic, etc. So it will be like this, it will be like that, until it reaches a steady state. That's a steady state. Steady state means change of the temperature over time is 0, and then I would reach at the steady state. At a steady state, I will reach to minus the second derivative of temperature with respect to x will be 0. Because at the steady state, change over time of temperature is 0. How about if we do not have case 2, is I have no conduction. If I have no conduction, then the process is pretty much convective driven. So that was case 1, which was no convection. And so I had all conduction. How about I have no conduction, which means now I am having case 2, which is convective heat flux. Then my change of temperature with respect to time would be plus r uf dt dx is 0. That's a special partial differential equation. It's still PDE because temperature is still a function of temperature and x, so it's PDE. First order PDE, by the way, it's only first derivative of temperature over x and t is needed here. And it's a hyperbolic problem. Hyperbolic equation. What does hyperbolic equation mean? It means there is a sudden drop. It's like a wave equation, which means if you had the same sample and you would have the temperature at higher temperature versus initially you had it fixed at a small t, right, frozen there, the temperature, high temperature value, which is at the T level, would move in your system with sudden drops. And this front of heat, hot water would fly in the system with the speed of RUF. That's the heat flux, heat velocity, RUF. That's exactly this coefficient. So convective heat transfer is a hyperbolic problem that is having sudden change. So this is coming, let's imagine you have hot fluid with now coming with the velocity RUF through your medium. And if you are standing here, you have no understanding of this type of heat flux until the carrier comes to you and you understand there is a hot fluid flying through this or flowing through this porous material. Imagine someone has thrown water on you and you have no idea, and then until it just reaches you, then you reach it. So that's wave equation or hyperbolic problems. What is the real case, real life? Case real. Instead of case 3, let me call it case real, which is both present, both convection and conduction present in the system, which would then mean that my temperature profile over time will be with RUF, change of temperature with respect to X minus conductive heat flux, D2T, dx2 is 0. Both of them are present. Now it will be a combination of diffuse temperature and sudden drop of the temperature. So how could you imagine that this can happen? If you have combination of a drop and a smooth because of conduction change. So you will get already this, but instead of, let's say, having a sharp drop, as convective heat flux would say, since you have conduction, it will smooth your front region and would make it to look like this. That's your temperature distribution when you have both of them. When you have both of them, convection and conduction in place, you have smeared out because of conduction, and you have a drop, a front that is traveling, and that's because of convection. The speed of it is still rho RUF, and you have a smeared out profile because of convection, because of conduction. So conduction smoothes or smears out the temperature profile. Okay, so this is qualitative understanding of the process. Now I'd like to do quantitative analysis. And so to understand exactly how smooth or how sharp the front of heat transfer is in my system, which means depending exactly on the ratio of conduction and convection, I can understand if my profile is more smooth, more diffuse, or sharper and sharper, right? So that is the next step study that we can do together to understand. Okay, this is the very final part of the lecture. Now, I like to solve this equation more quantitatively so that I can exactly plot this profile. To do that for more generic way, we introduced dimensionless form of the same equation. Now, if we introduce dimensionless time to be the time, typical time that I have, dimensional time, divided by, now I need something that requires a kind of a time scale, right? So then if I have L divided by RUF, since velocity is meter per second, meter divided by meter per second will be 1 divided by second, and so it will be, so I need it somewhere else, sorry, not divided by mode, but well, in a way I need it divided by in different ways. So I need it, this is meter per second. Oh, I'm sorry, that was correct. So I have L divided by RUF. How about the dimensionless length? Dimensionless length is actually X, the distance from my left, let's say, boundary of my porous material. That is also X as I have plotted it. So X can be any location here, divided by length of my porous system. So imagine I have a porous sample and it has length of L. Initially, it was as T initial, so initial temperature, and I am injecting T, for example, J, which is injection of, let's say, cooler or warmer fluid, injected fluid temperature, and I get some T out, obviously, in the system. So length is given. I know RUF is given, so there is a flux that takes place at a UF as well. And dimensionless temperature will be introduced as temperature minus the initial temperature divided by the injection temperature minus initial temperature. If I introduce the temperature dimensionless this way, when my temperature is Ti, so if T is Ti, then my dimensionless temperature will be 0. If T is Tj, my dimensionless temperature will be 1. So temperature will be always in dimensionless form, always between 1 and 0. Now, introducing these terms for dimensionless time, length, and temperature, I can rewrite my governing equation now for dimensionless temperature, X, and time, and distance, obviously. If I do the mathematics, and I invite you, please do so, and you couldn't, you let me know, but that's a very, very simple math. You find that that form of equation in dimensionless form will be change of dimensionless temperature with respect to dimensionless time. Then I have derivative of dimensionless temperature with respect to dimensionless space. And then I have the conduction part, which is then minus 1 over RUF L divided by D, derivative, second derivative of dimensionless temperature, and towards the dimensionless space, that will be 0. So what we did was we just scaled everything and introduced dimensionless quantities. In this system, my temperature distribution is always between 1 and 0. So that's the profile of temperature that I will get all the time. And my X dimensionless will be X divided by L, length of my rock sample or porous sample. So it will be always between 0 to 1 as well. Because when X is 0, XD will be 0. When X is L, XD, which was X divided by L, will be 1. Fantastic. Now, everything is dimensionless, including this coefficient, this factor, which is RU, some sort of velocity, times length divided by this kind of conduction coefficient, which is actually the ratio of convective heat flux divided by conductive heat flux or convection over conduction. That is defined as Peclet number, heat Peclet number. We will have it for dispersion, diffusion, and contamination also later on. But for heat transfer, convection over conduction gives us Peclet number for heat transfer. And therefore, I can rewrite my equation quickly as temperature derivative with respect to time plus derivative of temperature with respect to dimensionless space minus 1 over Peclet number, heat Peclet number, times derivative of T dimensionless over dimensionless space is 0. And now my question is, if I want to find out if I have Peclet number extremely high, that means 1 over Peclet, that means, therefore, 1 over Peclet is extremely small, it's almost 0, therefore it will be only convective transport. Convective heat is important, exists. So my derivative of temperature with respect to time will balance with the convective heat transfer point. When my Peclet number is extremely small, then my 1 over Peclet number will be very large, so I can neglect the convective part and go for conduction only. And that is why that I would be able to simply go along. Obviously, I can't do the derivative with respect to 1 over Peclet number. It's not possible. So what the system would look like? The system would look like more on the conductive dominated system, in which the second term here would be extremely important instead of this term. So I cannot really do the infinity here because division by a excuse me, division by a factor of infinity is impossible. We can't do that. What I can do is that I can assume that the convection is 0. So then I would only work with something like this, minus 1 over Peclet times d2 t dx2. In the dimensional form, that's the best. But this is not possible because, again, I have divided everything by d. When I have infinity, I cannot really divide by infinity. So that's not a correct mathematics for it. So I would just simply say approximately, or instead of just making it infinity, I would say, imagine Peclet is very small. Then 1 over Peclet will be very big, such that I can neglect, let's say, convection. Which means 1 over Peclet in this case will be much bigger than a factor 1, because that's the factor of conduction, and this is the factor 1. This is 1, which is the factor of convection. Now, I can actually solve this mathematically. I can solve it mathematically. There are many methods. Similarity solution, Boltzmann transform, it's Laplace transform as well, we can use to actually solve this analytically. If I solve it analytically for the porous system that I have shown already above, that would be this porous system that I showed above here. Then I am going to simply just write it again, that this is my porous system, for example, or I can write it actually in a horizontal way so that it will be even better. So I have a horizontal porous system, and then I know that I am injecting the Tj, I am producing the Ti or T out, and initially it was Ti. Dimensionless, I am injecting the T dimensionless 1. Initially, my temperature was 0, and I'm getting some dimensionless temperature out. Length of it was L. Dimensionally, dimensionless length of it was xt, which is 1. Now, if I solve this equation for any number of Peclet number, my temperature dimensionless as a function of the space and time dimensionless will be half of error function complementary of xd minus td divided by 2 root square td over Peclet number. That's the analytical solution of my temperature that fits this equation. If I want it to be dimensional, obviously I can write my xd to be, for example, x divided by L, td as well, etc., etc. Then I can find out what it is in dimensional form, but better is dimensionless form. Error function complementary is defined as integral 2 divided by root square pi, integral from u, from any number to infinity, e to the power minus u to the u squared du. That's a mathematical function. If I put it in Python, if I put it in MATLAB, it will give me the value. It's a value for any error function complementary of u. I can put it in here, and then I find the function there, the value of it. And that would mean that when I plot now my function of temperature dimensionless versus x dimensionless, which is from 0 to 1, and temperature from 0 to 1, I'll see this profile if I plot that error function complementary here. And then when I change Peclet number, which is the ratio of convective heat flux to conductive heat flux, I see the consequences of, let's say I can plot it with Peclet number 10. Now I can change Peclet number to be 100 or 1. And I can see the impact of it, whether it can make it sharper or it can make it smoother. Because Peclet number is convection towards conduction. And if I increase it, I increase convective force. Imagine convective force, so it will make it sharper. If I reduce Peclet number, then I am increasing the denominator, the conduction, so it will make it smooth. So if you have a profile of Peclet number 10 to be, for example, this is for example, Peclet number 10. If you make it Peclet number 100, convection is stronger, so it will look more like convective heat flux than conduction. So it will look like sharper. That will be the Peclet number, let's say 100, typically. You increase it, it will get sharper. You decrease Peclet number, it means convection is decreased over conduction. You get it smeared out more and more and more. I like you in the practical session, plot that function and study the impact of Peclet number in the process of how much convection conduction interplay exists and how does the temperature dimensionless over x dimensionless profile look like. With that, I hope that you enjoyed the topic of heat transfer in porous media and energy conservation, and are able now to find the distribution of the temperature in your system with the convection and conduction in the place. Obviously, more advanced topics would include condensation, evaporation, phase change, a lot of other things, but it's unnecessary. With these principles, you can study anything. So we started from atmospheric sciences. We covered about the temperature change over elevation. Now we went to subsurface and we found temperature distribution in our subsurface reservoirs. Now, with that, I'll be back to my slides. These are exactly the governing equations that I just handwritten for you, and with all the definitions that are all in here. So you should be perfectly fine with that. And then I studied the only convection or only conduction. If it is only convection, you will see sharp profile of temperature change in the reservoir over X. If you have only conduction, your temperature profile would be very much smooth like a parabolic function. And then we both together, we just did that by hand with my notes, and you understood that this system where you have conduction and convection all together, the system would look like more like this. So you will get it smeared out, but at the same time, you have a front that is transported. And then you have a temperature dimensionless, which is a function of time and space dimensionless, as half of error function complementary xd minus td over 2 root square td over Peclet number. And Peclet number was the ratio between convective heat flux to conductive or conduction. If Peclet is high, it means convection is more important. If Peclet is smaller, then conduction becomes more important. And so with the non-dimensional form, we have found that would be the 1 over Peclet number. Peclet number comes here, and then we can study that, and we find that the exact solution to this problem will be given by that error function complementary, and we just study that in our practical session indeed. I hope you enjoyed this lecture, and if you have any question, please let me know. Have a nice day, and goodbye.